Yes, that's right, that's right.
So, ladies and gentlemen, we are ready for the second session, and we are now turning to chemistry. And we will hear Professor Zewail speak about freezing time in a femtosecond, a very short time. And I will first give the floor to Professor Bengt Nordén, who will introduce the speaker.
Thank you, Mr. President. Ladies and gentlemen, it's a pleasure and an honor for me to introduce to you this year's laureate in chemistry, who is being awarded for his pioneering investigation of fundamental chemical reactions using ultra-short laser flashes on the timescale on which the reactions actually occur. Professor Zewail's contributions have brought about a revolution in chemistry and adjacent sciences, since this type of investigation allows us to understand and predict important reactions. Well, many of you are probably curious about how the Royal Academy of Sciences selects fields and persons in the specific cases, and what discussions have been preceding the decision. Now, according to the fundamental regulations of the Nobel Prize, this information is secret and may not be disclosed until 50 years after the decision. So this is the official motivation for this prize. But I think, dear Professor Zewail, I would like to promise you to tell you everything. Just wait 49 years and 10 months. Well, you laugh. I think you should not laugh. I think this is highly plausible. You have here a healthy, young specimen of man. Somebody's mobile phone I heard just now, and we have also regulation that if somebody has forgotten to switch it off, he has to pay for beer for everybody present. So born in Egypt in 1946, Ahmed Zewail had his basic university training at the University of Alexandria, whereafter he moved to the United States, where he got his PhD in 1974 and passed various positions, got his full professorship in 1982 and the prestigious Linus Pauling Chair at Caltech in 1990. He is, since some years, also director of the National Science Foundation Laboratory for Molecular Sciences. And he is also a member of the National Academy of Sciences. And he has a long list of awards, the prestigious Welsh Prize, the Wolf Prize, the King Faisal's Prize, the Benjamin Franklin Medal, which, by the way, both Marie Curie and Albert Einstein got. And, well, there are more than 25 prizes, and I think many of these he would not have received had he received the Nobel Prize earlier. So, well, as a matter of fact, I couldn't remember all the prizes, so if you read carefully, there are lots of strange prizes here that I just invented, and I will not read that, but I'll show you, Ahmed, later. My students were very alarmed when they saw this. So I've tried to find out something about this fantastic scientist's hobbies. Does he have any private interests, any hobbies? And I can't say that I've succeeded, but I found out that he might become a stamp collector. His face is on the an Egyptian stamp, and when I told my student that, they became very inspired, and they thought that maybe we could have a Swedish stamp with his face on as well, and this is the result. To be serious, I think Ahmed has one big hobby, and if I'm not wrong, that's science. And well, he will tell you more about that now in a few femtoseconds. He will tell how to freeze time in femtoseconds. Please.
Thank you so much. Thank you so much. Thank you.
Before I leave the stage, I want to give you a small present, which I put here. We usually do this when we haven't taken the final decision about the prize. We want to have a final intelligence test. And I hope that you shall be able to use this at some instance in your talk. And it consists of two pieces, this thing and a small ball here. Okay.
Well, before you leave the stage, one thing is very good about this. In the bylaws of Mr. Nobel, they don't take the prize back. So no matter how I fail here. Thank you, Ben. Well, it goes without saying, it's truly thrilling to be receiving this award. It's an award not only for me, it's an award for the entire field, shared by colleagues all over the world, and in particular by my own non-biological science family at Caltech, which total close to 150 people, as you will see at the end of my talk. The Nobel Prize, once it was announced, our phones and faxes and emails and everything was jammed, and all kind of wonderful articles all over the world. But I thought I'll tell you also something that comes with the Nobel Prize before I start my talk. And this is the only slide of transparency I'm going to show hiding something from you. But this is the, it was a physics magazine published in Europe, and it got the first part right here. It's Zewail received the 1999 Nobel Prize for chemistry for the development of laser-based techniques that allow the motions of atoms inside molecules, and goes on and on. And it's basically, they took this out of the wonderful write-up that the Academy here has produced. But then I kept reading, and it said, Zewail was born in Egypt in 1496. And so I thought it's really credit for the Nobel Committee to give me the prize after 500 years. So that's what you get from some newspaper sometimes. Yeah. Well, what I would like to talk to you today about is the idea of freezing time in all the way to femtosecond. And I have to apologize up front to the experts in the audience, because my audience today are going to be the students in the audience, so I'm not talking to the real experts here. So this have a beautiful history that I'll share with you in the beginning, but just to start, let me get into some numbers here for the students. In the middle here, this is 1 second, which is, we call it 10 to the 0, 10 to the power 0. The pyramid is built this way, that if you go to 1 hour, then we're talking about 36 hundredths of these seconds. If you go to 1 year, it's actually 32 million seconds. 1 millennium is 32 billion seconds. And if you go to 1 million years, then you can see the number of zeros that you are here, 32 million years. And finally, if you go to 1 billion years, is 10 to the plus 15 second. As you can see, you have 3, 6, 9, 12, and 15 zeros. So as we go to billion years, the power that we have here is 10 to the plus 15. On the other hand, there's a whole other world which we try to shorten time from 1 second. And so if we divide by the same idea in a down-going pyramid, then if we divide by 1,000, we are in the what's called the millisecond. If we divide by 1,000,000, we are in the microsecond, and then the nanosecond, and the picosecond. And finally, at the femtosecond time scale, it's a 0, and then here we're dividing by 1 over 10 to the 15th, which is 10 to the minus 15. So you can see we are going by about 30 orders of magnitude as we go from the top pyramid to the bottom pyramid. And what the Nobel Committee might not have known is the fact that these terminologies here, the milli, micro, nano, and pico, it's actually comes from the Latin and Greek and the Romance languages. But finally, they couldn't find anything appropriate, so they went to Scandinavia and got femto. And this is, maybe that's why I got the prize. You never know. To see that this is just a snapshots, now that you are expert about 10 to the plus 15s and going from billions of years with the beginning of the Big Bang and actually the formations of these galaxies and all the way to our existence on the Earth, about 4.5 billion years. Here is human civilizations, and of course, I'm putting Egypt here. It's 4,500 years ago. And then the important one I want you to watch is your heartbeat. And this heartbeat takes place on the second time scale. But if you want to go less than the heartbeat, in fact, it's believed that Galileo used his heartbeat in order to time events in the physical world. But if you want to go sub-second here and see what's happening, then, for example, your eye responds in about 50 milliseconds. But by the end of the talk, I want to get you by about 10 orders of magnitude down, because the molecule in your eye right now that's seeing me is actually transforming a signal into the brain in 200 femtosecond. So in order to go from a second into the femtosecond, we need a whole 10 to 12 to 13 orders of magnitude in order to see this whole new world of molecules that we are interested in. Well, the history of measurements of time is very rich, and I just took 6 snapshots, which will be in my Nobel lecture or Nobel article, and obviously I am leaving in between an enormous contribution. There are books and books which will be referenced in the full article. But fundamentally, the first concept of defining time in appropriate way came 4,200 years BC, which is the invention of the calendar, which actually happened in the land I was born in. The scientists of the day used to watch a very famous star called the Sirius star, and it has a meaning for the flooding of the Nile. And by watching this star, they could determine that the number of days in the year is 365 days. And in fact, it's remarkable that 6,000 years ago, they even could come up with the concept of the leap year, because every 4 years they added 1 more day in order to have the solar calendar properly tuned. About 1500 BC, both the sundials and the water clocks were invented, and this is an extremely important idea because now we defined an hour in the day. So we went all the way from the year into the hour of the day. And of course, the mechanical clocks around 1300s in the Western world was invented to look at minutes and seconds. And up to here, this is consistent with our physical sensing of phenomena. But in order to see something in the sub-second domain, this was the first brilliant idea, and it has a history in its own right, which if you are interested in, you can see it in the beautiful poster here done by the Swedish Academy of Sciences. And there is the first time that a galloping horse was photographed in real time. So the camera or the shutter speed had to be lower than a second by a factor of 1,000, roughly. So this is a millisecond camera, and it freezes this horse during the motion, and this is actually the snapshot. And what Muybridge, who invented this method, did, he took different snapshots of the horse, and if you fool your eyes by making 25 frames or 30 frames, then you can actually see the horse in a movie picture. That was actually the birth of this idea of creating a motion picture of objects of that type. Going from the milliseconds to today's 1980s femtoseconds, as I mentioned earlier, we're going by 12 orders of magnitude in order to be able to reach into this world of molecules and see the true motions of the atoms inside the molecule. And so, with this in mind, you might ask, what's that good for as far as chemistry and biology is concerned? So I digged into history, which is my hobby, and I thought you might be intrigued to know that this actually, Mr. President and Chairman, this actually is a new museum here. And this is called the Stockholm Papyrus. This was the first time that it was recorded of how a chemical change have taken place. It's translated into Greek and kept here in Sweden, and so I have a Greek friend that I asked him to, at Caltech, that I asked him to translate this. And you might find this a little bit strange, but I think it's intriguing to tell you what chemistry was about 3,000 years ago. So, what this document say, mix together and put into a pot 2 grams of malachite, 2 grams of azurite, 100 cc of the urine of a young boy, and 100 cc of a solution of oxygol. Put into the pot all the 24 pieces of stone, each weighing 0.27 grams. Put the lid on the pot and lute it around with clay. Heat for 6 hours over a gentle fire of olive wood. It has to be apparently olive wood for some reason. When you see the lid had become green, do not heat anymore, but allow to cool and take out the stones, when you will find that they have become emeralds. That was the chemistry, probably the organic chemistry of 3,000 years ago. Now, of course, they did not make emeralds. They were just simply coloring this beautiful color stone. So this was chemistry thousands of years ago. Chemistry made a major jump by this French scientist, when actually they were on a mission. Napoleon was on a mission on Egypt, and it has a beautiful history because in the laboratory, it was very well known in those days that if you take sodium carbonate, we teach you this in classes, sodium carbonate, and you mix it with calcium chloride, you make the table salt plus the limestone. That was proven in France at the time in the laboratory. However, they noticed when they were on the Natron lakes, Wadi Natron, they noticed that what they see is the fact that the salt and the limestone react and produce the sodium carbonate and the calcium chloride, which is the reverse reaction of the first one that they were seeing on the laboratory. So the laboratory experiment was giving well results. The lake, or on the lake, they were getting other results, and that established the concept in 1798 of the equilibrium hypothesis of chemical reaction, meaning that what can go forward, it is possible also to go backward. However, it was only 100 years ago, in 1898, that the Swedish scientist Svante Arrhenius have told us in a brilliant paper published of how to think of the speed at which either the forward reaction or the backward reaction is going. And what Arrhenius have shown is that somehow these atoms and molecules have to fight with each other at a given temperature, and in these violent interactions, the atoms will get close to each other, but they must climb up a mountain. And in this mountain at the top, he called it a compound state, or nowadays known as a transition state. So somehow that the reactions, as they go from the initial phase, which is reactants, to the final phase, which is the product, they have to go through a transition state. And that's not too different from our existence on Earth as humans. We all go through transition states. So Arrhenius put a simple and beautiful equation that's used almost by every chemist and biologist when they think of the speed of a chemical reaction. But of course, he had no idea of how these atoms move and what is the speed. So now I take you right into the femtosecond world and tell you what the Swedish Academy called the fastest camera in the world. This molecular camera, which gives us into the atomic scale motion that Arrhenius was dreaming of to understand. Namely, it turns out, and there is a fundamental reason for this, the speed or the velocity at which the atoms in a molecule, in the course of a chemical change, typically it's about 1 kilometer per second. So in 1 second, you sweep a whole kilometer. On the other hand, the distances between these atoms in the molecules are angstrom, or 10 to the minus 8 centimeter. So if you combine the speed and the distance, you come up with a time which is 10 to the minus 13 second. And that's 100 femtosecond. The state of the art right now in time resolution that the world has achieved is 4 femtosecond, 10 to the minus 14 second. Therefore, on this time scale, we can actually freeze any molecular or atomic motions inside the chemical change and watch the evolution as these atoms fight with each other and form a chemical or biological chain. And my students who do all of this, because I am totally ignorant of how to do this computer fancy stuff, they put this, it's like the big bang of femtochemistry. That is the beginning of femtochemistry. Because of this fundamental idea that this is really the limit of time as far as the motions of atoms and molecules, the field in 10 years' time only has really exploded. And as Professor Norden said, it really had been a revolution in the field, meaning that it have expanded all the way from isolated chemical reactions to the mesoscopic phase, where you study clusters, droplets, nanocavities, nanoparticles, nanorods, into the condensed phase, dense fluids, superfluids, liquids, solids, surfaces, and so on. And also it have now made a major, actually, contribution into the area of femtobiology. And at the end of my talk, I'm going to tell you about where the future is going to be. The studies have included elementary phenomena, such as the transition state that I spoke about, how energy moves in the molecules, and also what's called the microcanonical rates, which is very important for theory. Essentially, all chemical bonds has been studied. The covalent bond, the ionic bond, dative bond, the metallic bond, hydrogen and van der Waals, all of this. Molecular sizes. The studies have been including now, we started with 2 and 3 atoms. In fact, one of them is here that I will show you. And the field has gone into DNA and proteins, and with major contribution from all over the world, including contribution from here in Sweden. And the states of the system can be either the ground or the excited states. It could be neutrals or ions. All of this has been done by many colleagues. After the Nobel Prize was announced, there is an institute in the United States called Institute of Scientific Informations, which tracks all citations. And they are very proud to point out that they were ahead of the Nobel Committee in pointing out that the citation of a field is an indication of what's going on, and they send me this transparency. So this is not mine. The credit here is for the Institute of Scientific Studies. in Philadelphia, and they pointed out that since '87, where the breakthrough was done, and in 1999, there has been 50,000 citation for the field. Even Japan is committing itself right now to $250 million in order to get to femto. This is 120 million British pounds, and they are going with a variety of methods to control matters and so on. But how did we get into this? So I want to share with you first our struggle in the early days, because we didn't know what we were doing, really. Our struggle in the early days brought a very important concept to all of this that you will see it was difficult, especially for the chemist, to appreciate in the beginning, and that's the concept of coherence, which I'll get to. Then we had to marry both ultra-fast lasers into molecular beams in order to isolate in the early studies these reactions and these molecules from the rest of the world, so we can study the atoms without too much perturbations that takes place. Then we had the femtosecond dream, and then the cornucopia of the field, and some impact and concepts that evolved. So the first experiment was mind-boggling for us and opened up our eyes to the phenomena. There was a feeling that if you follow Arrhenius' ideas of heating the reactions, and you have a finite temperature, that essentially all molecular motions will be treated in a very statistical way. There is no difference between one motions versus the other. So we thought that by these new techniques that we were developing, on those days we were in the picosecond time domain, that we will excite large and complicated molecules with a picosecond time resolutions of pulses, and then we will look how the vibrational motion in these molecules. If it's really temperature and the molecule is becoming hot, then the energy should distribute into all other modes in the molecules very quickly. And that's what every chemist will assume, the so-called statistical behavior. On the other hand, if there is a well-defined coherence in the molecules, which you will see how it was exploited, then maybe the so-called the entire phase space of the molecule is not being utilized. So to our pleasant surprise, we were just trying to measure how fast the energy is going to move in the molecule, and this is a message to the students. Not everything is planned and not everything is brilliant to prepare. This was actually something we did not expect. We just wanted to measure the time, in real time, how energy is going to move. But instead, what we found is that the energy is leaving certain modes and coming back, going up again, coming back. It's like a birth of a baby and the death and birth and death, and that just is not what we think of these processes in molecules. We thought that this would be simply a decaying process describing how the energy is moving. And in fact, as we monitor where the energy was going, there was a complementary behavior. Where the energy was in this mode of this molecule maximum, it was minimum in the other mode. So clearly we know that the energy is going back and forth between two modes, two vibrational modes of the molecules, even though we have million states in one wave number, if the physicists are in the audience or the chemist. So that means that out of all of this mess of a complex molecule, we have found and discovered that you can see order and coherence in these molecules. And we wrote a paper immediately that was published in the early 80s, and in this paper we called it was published in Physical Review Letter, and it was called Direct Observation of Non-Chaotic, you're seeing order now in these molecules, non-chaotic multi-level vibrational energy flow in isolated polyatomic molecules. Peter Felker now is a professor at UCLA. And this is the concept for the physicists and for our advanced students. That's actually is a two pendulum here. Just imagine you have one pendulum and the other, and they are connected by a weak a spring, and all what we did, we kicked one of them on the picosecond time scale. But what's amazing, this is in a sea of many other vibrational modes, but yet the energy is moving back and forth between these two modes as if they don't know about the rest of the molecule. That's a beautiful coherence and order that opened our eyes to the idea, to a new idea that was not perceived before. So we immediately, and of course, thanks to the technology, was advancing very rapidly, and we immediately then introduced the idea of going into, by the same techniques, into the femtosecond time domain. But we had a problem in the femtosecond time domain, and that is you can't measure the response by electronics. These are very fast clocks now, millions of a billions of a second. So we used an idea, which in fact I digged into it, and it was first converting distance into time using light. And this was done in a brilliant demonstration in the 1800s by two French scientists. So the idea here is that we know that the speed of light is huge, and so by delaying an optical pulse of a femtosecond shutter speed or duration relative to another one, if you make this distance separation of 1 micron, which we can do nowadays, you create 3.3 femtosecond. So that means that if we use one of these pulses to initiate the chemical change and then delay a whole series of pulses, each one by a micron, which will be 3.3 femtosecond, we can take a real snapshot of what goes on in the chemical change as a function of time. And the resolution now is in the femtosecond time domain. The detector, as you will see, could be a variety of things that we and others have developed later. What you see here, this is the fastest camera. It might appear too complicated, but nowadays actually you can buy these lasers in a very straightforward way. And this was the first laser built by us following a design that was made at AT&T. And here we amplified the pulses ourselves, and we can create a white light continuum generation. And by using these two pulses, one to initiate the change and the others to follow what's happening, we can take what Muybridge did for the horse, but now for the molecules with the atoms moving, and we can take as many as 1 million frames if we wanted in order to see the complete change that we have there. This is just to impress you by color graphics, so I'll just take it out. And then here what you see is that a variety, how do you follow the motion actually itself? And the motion, we started by what's called the laser-induced fluorescence. So we're looking at fingerprints, at the colors of these atoms, or the music that they send out as a function of time. And we can look at their spectrum, or we can look at their mass, how the mass is changing as a function of time. We can look at electrons coming out, as you will see. There is a whole variety of things. And if we want to go to the ground state reaction, the equivalent of thermal reaction that happened in the laboratory, we can use infrared pulses and a variety of other techniques here on the left. And at the end, I will tell you about something new that we are interested in. But I just want to share two concepts with you that were very difficult in the beginning of the field for people really to appreciate. One is the time resolution. And there is always the suspect, what do we learn? What's new? My own feeling there, stated here, is that every time we improve on the time resolution by a factor of even 100 or 1,000, we must be able to see new phenomena that we did not even think of. So I was pushing very hard to get into the femtosecond time domain because I really believed that because of the fact that the atoms are moving in kilometers per second, there got to be a whole new world there that we can understand what's going on. But as important is that we can get into the atomic scale dynamics. Now, Mr. Chairman, Manfred Eigen, in his Nobel lecture in 1967, that I took from Le Prix Nobel, and Eigen himself thought that that's the end of time resolution. So this is his title for the Nobel Prize in 1967, and I think he termed this the fastest chemical reactions. And his belief, Manfred, that this was the time scale of chemical reactions. The distinguished George Porter, who shared the Nobel Prize in 67, he actually wrote this statement in a book published by Sweden, in Sweden, saying, in looking at possible future development, it would be easy to suggest that there will be subsequent meetings where interest centers on the picosecond and ever shorter time intervals, but I think this is not very likely. Surely, it will become increasingly possible to carry out experiments in these shorter time regions, but what we shall begin to experience diminishing returns as far as the study of chemical reactions are concerned. Now, I would not be standing up here if this was the case. The time scale there was in the microsecond, and there was a feeling at the time that that's going to be the end of the time scale. But George, who's a friend, now is Lord Porter, wrote a very wise statement recently. He said the study of chemical events that occur in the femtosecond time scale is the ultimate achievement in half a century of development, and although many future events will be run over the same course, chemists are near the end of the race against time. But that's natural. We all change our minds because obviously new technologies. In fact, when I teased Manfred Eigen about this in Göttingen, he mentioned to me that nobody anticipated the invention of the laser. And so one has to be very careful about supporting basic research and being very visionary about the support of basic research. This is just a brief summary of some milestones here in the arrow of times, especially in chemistry and biology. You have the ability, we have the ability as humans to record reactions from the seconds because of our eyes and up to our lifespans of about 1 billion seconds. So that's the slowest chemical reactions you will be able to watch. But it was around the beginning of the century in a very important experiment on the hydrolysis of sucrose that the first kinetics was done with sub-second time scale. And Arrhenius, of course, who was part of it, and Van 't Hoff. And then in around the 1920s and 40s, the flow methods and stop flow methods, you mix two reagents and you see how the reaction is going to proceed. And this is what I mentioned to you about the microsecond by Eigen and Norrish and Porter. And then the laser came on the scene. Nobody anticipated that this is going to immediately give us the nanosecond time scales. Very shortly, it became a picosecond, and now we are in the world of the femtosecond time domain. Now, why the atomic scale resolution was a problem? I recall 10 years ago, every time I give a lecture, especially in front of the chemist, somebody will stand up and say, what about the uncertainty principle? You must be violating the uncertainty principle. And the idea that was really difficult to see is that it is very well known from Heisenberg equations that if you shorten the time too much, it will be on the expense of increasing the energy resolution, which means that you lose information in the energy domain, because these two are related by a fundamental constant, which is Planck's constant. So I just want to take you through a few transparencies. Through the idea of this coupled with the concept of coherence, we can get around completely this misleading concept of losing the information. And in fact, we can get into the idea of single molecule behavior on the atomic scale. This, by the way, was a hot debate among physicists in the 1920s, because Schrödinger have solved his equation, the famous equation, and in solving the Schrödinger equation, the wave functions is extended over the whole molecule. It's called the probability distribution function, if you like. And in those days, they wanted to connect with Newton's mechanics that we all know. Momentum changes in a collisions, distance changes, and so on. So Lorentz, I found this, wrote to Schrödinger on the 19th of June, 1926, and said, This is the reason why it seems to me that in the present form of your theory, speaking to Schrödinger, you will be unable to construct wave packets that can represent electrons revolving in very high orbits. Because Schrödinger wanted to show that under certain conditions, his equations, his wave equations, will go into Newton's type behavior if this was true. And this paper is extremely illuminating because it's a paper by Schrödinger, which I copied, and it's only 3 pages. And I bet if this paper was published nowadays, it probably would be 30 pages in order to say the same thing. But what Schrödinger have pointed out here is that if you take all these wave functions and you superimpose them coherently, he didn't say coherently, but if you superimpose these wave functions here, you create what the physicists know very well, the wave group or the wave packet. And one thing that's very important about this, that they are localized in space. So the key idea in our approach was to follow in the footsteps of concepts that de Broglie, Schrödinger, who got the Nobel Prize, have related the behavior of waves, matter waves, and particles waves to each other. And as I showed you with Schrödinger, now we're talking about going from micro to macro mechanics, from quantum mechanics to Newton mechanics. And so all what I'm showing you here is a back of envelope calculation that if we were to look on any molecular system of interest to us in a fundamental way, you cannot just use the energy and time uncertainty. If you use in connection also the momentum and distance uncertainty, which is obvious to you have to, then you actually, even for a force-free motion, you find that there is a very simple relationship between time and distance uncertainty. And if the time resolution is 10 femtosecond, you can localize this nuclei to a better than a tenth of an angstrom, much less than the bond distances between the atoms. On the other hand, if the time is 10 picosecond, then the distance resolution you're going to get is about 100 picosecond, 100 angstrom, and as a result, you cannot see any motion in the molecule. And that was a key concept. A, we want to prepare the system in a coherent way, and B, that we can exploit the time resolution so we can truly create an atomic scale resolution without violating any of these concepts. And this is a theoretical calculation that was done after the fact. The experiments was done by a former postdoc, Martin Grubele, who's on the faculty now at the University of Illinois. And what Martin did here when he was at Caltech is that we take 2 atoms with 1 bond. And if you take these 2 atoms and you ask, what is Schrödinger wave equation will be like? It will give you all of these nodes here, and it tells you that the system can be anywhere in space. The energy is very well defined, but the distance is not well defined. You are over the whole map. On the other hand, if I looked on the same system on 10 femtosecond, the entire system now is localized at this particular distance, and now for the first time we can speak of the molecular system as a spring that's localized at this distance, and then it can stretch and go to this distance and can execute motions depending on the potential and the forces that's holding the atoms together. And the beauty of the femtosecond from an experimental point of view that the expert in the audience will recognize, this is an experimental 2-dimensional image of what a pulse in the femtosecond will look like. Here is time, and here is the energy uncertainty determined by the wavelengths. And you can see, even though we have this energy spread, but all energy components come at the same time. So we call this transform limited pulses, meaning that they are coherent enough to excite the molecular system in a coherent way and start the atomic scale motion that we are interested in. One of the first experiments that we did to demonstrate this on bound systems was to take 2 atoms connected by this weak spring. And by the way, we're dealing here with millions of molecules, but because we are exciting them coherently, they are all behaving as if they are one molecule. So now here is a spring stretching, compressing, stretching, compressing, and so on. That's what is in our image as Newton would have imagined what's happening in these molecules. If we have done it with quantum mechanics, the whole system, you have to solve the Schrodinger equation and write the expectation value and all of this and find out what does this mean. But now, if we look at the femtosecond time resolution, we are not losing energy resolution anymore. And in fact, what you're seeing here that was published a long time ago is that signal that's indicating that the spring was compressed, stretched, compressed, stretched, compressed, stretched, and so on. And so going back and forth, indeed, as if we have particle behavior of that spring motions as the atoms move in real time, you're taking a snapshot of the entire motion. And from this, you can get actually the real potential and the force that the atoms are experienced, and this is indicating pictorially what's happening to the atom in the course of the change. Immediately after this, we recognized that we can also orient the molecules in the laboratory on the femtosecond time scale. If we wait long enough for the molecule, they will randomize. But now if we catch them on the femtosecond time scale, they will all line up, essentially line up, and then we can see how they can get away from each other or out of phase, as it's called, and then we can watch them coming back in phase again. And this turns out to be quite powerful because it gives us something about the molecular structure. If you know how long it takes a molecule to rotate in space, you can actually derive information on the molecular structure. And this has been done in our laboratory and in Peter Filker's lab when he went to UCLA. And I just show you very complicated molecules that from these ideas of orienting this molecule in space, we can obtain their molecular structures as well. But we were after the black box, the transition state of how a system is going to transform from the reactants to the products. I showed you now with certainty that we can see the atomic motions. But how can we go from the initial state of the system to the final state of the system and open up this black box, which all of it on the atomic scale occurs in less than a picosecond and more than a femtosecond? So we first experiment, which was published in Journal of Chemical Physics and then in Science. First experiment was to take 3 atoms, and to my amazement, in retrospect, when one thinks about this, this is really remarkable that even though chemistry is all based on bond making and bond breaking, there has never been a real view of a chemical bond being broken or being made. So when we started with this, we thought it would be very interesting to take a 3-atom system and then to break one bond, the one between the red atoms and these 2 atoms here, and to watch in real time, just like I showed you, how they will separate from each other to infinity, and how these 2 atoms, as they come out from these atoms, because of the forces, they're going to rotate in real time. And this was done in this famous experiment, which actually the Nobel citation mentioned. And by so doing, we were able to clock for the first time the atomic motion of a chemical change as they actually occur in real time. But this is Linus Pauling at Caltech, and I like this because it shows Linus's interest in molecular structures. We are now in the age of molecular dynamics, and Linus was worrying about things like the table salt, sodium chloride, and covalent bond between 2 atoms and so on. So I was intrigued by his simple description. Nowadays, of course, quantum mechanicians in the audience, the experts in the audience, and last year Nobel Prize, you can do much better than Pauling have done in terms of valence bond approach. But this a simple enough system that one can say that the chemical bond is made of a contribution of a covalent contribution and an ionic contribution, what Linus called the valence bond description of the chemical bond. So we wanted to do this in the femto age that we are in, and with the Swedish Academy permission, I took this from their press release because they wrote much better than I did in our paper. So we had now here the 2 atoms that we decided to do. This is just like your table salt, but instead of the chlorine, there is iodine. And this turns out to be a paradigm case for the whole field, because you will see that in a minute. And basically, the ground state is an ionic the sodium is plus and the iodine is minus. But also there is another one here is covalent, where the sodium and the iodine are sharing electrons between them. And so this is a beautiful example of how a chemical bond now, in real time, should be transforming from being covalent, going to being ionic, and in fact, seeing the reformation of the bond again as it goes back and forth here, with some probability that the bond will be broken. And what we saw in the experiment was quite remarkable. And to this day, after 10 years now, from this first experiment, I still reflect on this experiment because it's extremely rich in what it's saying. What this experiment showed us here is that is this focused here? What this experiment showed us is that if we prepare the system on the covalent side, and the atoms are separating now until they become ionic and they bounce back, we can see this resonance motion. Here the system is covalent, here the system is ionic. Excuse me. Going back to covalent, ionic, covalent, ionic, covalent, ionic, and every now and then there is a finite probability that the bond is broken by forming the sodium plus the iodine. But what is extremely important about this experiment, that the whole ensemble, we have about 1 million molecules here. This 1 million molecules here are not behaving one at a time in a random way. And the reason for that is that we prepared all of them coherently as a wave packet. So even though they are million, they're behaving as a one molecule trajectory that's moving all together, glued, such that we are able to see the atomic motion with this resonance. If the ensemble was behaving randomly, we would have never seen this resonance, and we just simply have seen a decay, like it's called in chemical kinetics. And Professor Nordane was kind enough to give me this gift, which they had to do to justify to their own children here in Sweden why they give me the Nobel Prize. So this is now the 1 million molecules are now all glued together because we prepared them coherently. So we made a big ball out of this, and then you start the ball here on this bond being covalent. And it's going back and forth as resonance, but we'll do even something more exciting. So the resonance can go back and forth for many times, and we can watch this in real time. Of course, this is in femtosecond we're watching. But if you start this, for example, see? It's really brilliant. Really brilliant. Really brilliant. And so you can see the whole motion as an atomic scale, and even though we have a whole ensemble of atoms, one can, or molecules, one can see the difference. Of course, the quantum mechanics after that, just to prove that we are in the classical regime of the motions, we did the quantum mechanics, and in fact, Jorge and Matthew from Santa Barbara have done a very nice piece of work on this to calculate from first principle how the wave packet is going to move, and indeed it is a classical motion on the time scale. My colleague at Caltech, Professor McCoy, have done the state-of-the-art now in dealing with the quantum mechanics of this system of the two atoms, and what you're seeing now is the landscape both in time and distance on the angstrom scale, and I apologize that Vince did not put the correct O here on the angstrom. And then you can see the wave packet is moving back and forth and doing the resonance, but every now and then there is this motion going out on the landscape to break the bond and make the sodium atom and the iodine atom. And the remarkable thing is the wonderful agreement between theory and the experiment in a fundamental way. And we were thought that we were done by this, and the whole world is done by this, but of course there are hundreds of papers written on sodium iodide, because one of the intriguing things as a physics exercise is that after the motion was done and we thought we understand what's going on, if we waited even for a very long time, this is now in the picosecond time domain, we actually saw the entire motion recurring again with a beautiful phase relationship, and this is called recurrences, and in between here there is random behavior. So it's a very fascinating physics problem that I will not dwell on here too much. But can we do the same thing now? The complexity have to increase. And that's what we have done. Can we go to Arrhenius' dream, 1889, in this famous paper? Well, in Arrhenius, you have to cross a barrier. And so we choose two nuclear motions, two coordinates, and here we have 3 atoms. And in these 3 atoms, we can now prepare a system with distances known from the wave packet, and then we can see again how the atoms are going to separate one atom from diatoms, or diatoms from atoms, or all atoms will separate. And by so doing, we can understand this barrier crossing that it took 100 years to be able to see in real time. Then we went on after this to do what's called bimolecular reactions. In chemistry and biology, there are 2 reagents that can come together, and then they form a bond and break bonds, and we wanted to also see this in real time. And this is one of the classic reactions in the upper atmosphere and in combustion. When you are sitting next to your fireplace, actually this is what you're seeing in this chemical reaction, one of the chemical reactions. And so we decided to create a hydrogen atom in femtoseconds and let it react with carbon dioxide to monitor the dynamics of what's happening in the transition state region as these atoms get together and form and break chemical bonds. The theory, of course, is extremely challenging, and some of the ab initio have been done. But I thought this is artistic piece here was given to me as a gift. As the field started, and we had here basically the elementary reactions and transition states. But then we had to move very quickly into more complex systems. We actually entered this area by organic chemistry, which is a very, very rich area because the molecules are very complicated and complex enough to allow us to look for a variety of phenomena, as I will skip through some of them. And then we went into the mesoscopic phase, like nanostructures and clusters. This is our own work. There are a lot of people did other things, but I'm just mentioning here how we branched in this area. We went into condensed phase by the idea of using dense fluids and liquids and some polymers work that has been published recently. And then at the end, I'll tell you where we're going. So just to give you an example of something that we were interested in, how do you deal with systems that are quite complex? So we thought almost 6 years ago of interfacing what's called mass spectrometry into the femtosecond domain. So here now, we can actually see the masses of the individual species as they separate, form, and break and chemical bonds. And we introduced this idea of the 2-dimensional array, which you have time on one axis and mass on the other. And in fact, one of the people that were involved in this heavily is Jennifer Herrick, who is now on the faculty at Lund here in Sweden. And what you're seeing here is that, in fact, you can look at some molecules like these and ask questions that just we could not dream of asking even a century or even 10 years ago. For example, this is acetone, which is a good nail polish remover here, and it has 2 bonds of identical symmetry, and now for the first time we can ask, are these 2 bonds breaking at the same time, or one of them is forming an intermediate species followed by the breakage of the second bond? We can ask questions about, I used to learn this in school in Alexandria, that a reaction like this, you do a bookkeeping of making these arrows until you get the products. But now we can provide you with a map that the first thing happened that the proton moves in 90 femtosecond, and then you form this diradical species, which breaks then to make ethylene plus the enol. So you can really understand in great details the mechanistic basis of the concept why the reaction proceeds this way or that way. This was on the cover of Science because I think it's one of the beautiful example of demonstrating that on the femtosecond time scale, we can freeze reactive intermediates. The landscape here is very complicated, and we're forming one of the most important reactions of condensing 2 ethylenes to make cyclobutane. But there are many discussions, do you form intermediates on the way out in this landscape? And we were able to freeze this in time and compare theory with experiments, and with theory actually done here at Lund in Professor Roos's group. We can provide for this particular species what's the time scale for fragmentation, rotation around bond, and even cyclization as the system form and break chemical bond. We just submitted a paper which was accepted about some molecule that's very important as an anti-tumor molecule for cancer. But the mechanism, the nature of the transition state was not clear, so we actually started a collaboration with my colleagues, the organic chemist, the distinguished organic chemist Jack Roberts, and we can actually now prepare this precursor and look at this transition state of a benzene species that's involved in a Bergman rearrangement. So, following this, we decided to go to the mesoscopic phase from clusters to nanocavities, to polymers and interfaces, but I don't think I'm going to bore you with the details, so I'm going to skip many of these details, just to point out that one of the interesting also applications by others that you will see in this physical picture is now the combinations of the time resolution and the spatial resolution. And this is coming on very powerful in surface science. And I think if we wait 10 years, we will see major discoveries made on surface science with atomic scale resolution, but also getting the time resolution of the dynamics as well. Well, what about the biological? If you look at the biological, we ourselves have been involved in some of the things I just mentioned briefly, the anti-tumors. We have been involving in understanding some of the mutations that creates mistakes in the genetic code and what's the time scale for such motion. But I'm going to pick up just one example and another from other colleagues. And one major problem in biological activities is electron transfer. This I got very much interested in, started by looking at photo attachment and photo detachment. And in fact, Professor Eberson actually have written a book on such processes and whether or not they are concerted or not concerted. So we started this with a modest systems, and now we have done something in the biological area that's quite exciting. The modest system was probably your grandmother, if it's like mine, if you if you have a cut in your hand or something, they used to use iodine or something of that sort. But it's well known that iodine, if it's dissolved in benzene, it changes its color. And it was discovered in 1889. But until very recently, we don't understand the mechanism by which the atoms are behaving as the iodine and benzene react with each other. So we decided to introduce this new technique where we look at the time scale from femtosecond and on, and also the speed at which the atoms are coming out. And this we can do nowadays in a very clear and correlated way. And the bottom line here is that you can actually take snapshots. And even my student, Dongping Zong, who did a marvelous job on this, in his thesis on this, he can actually put a clock here, but in femtoseconds. And here is the conjecture was, what will happen as we have the iodine with the benzene, and we can isolate this now from the rest of the world and add the benzene one at a time. But first, the electron jumps into the iodine and there is a charge separation. But unlike what everybody thought, actually the electron jumps back in about 200 femtosecond, leaving the iodine snapped on the top of the benzene, and one atom comes out first, which we can detect at a given speed, and then the other atoms comes out later, and we can map out really both in terms of structure and dynamics what is going on. And in fact, the original proposal was that iodine lie down on benzene as this way. In fact, we found that the iodine is actually vertical on the top of the benzene, and the angle is about 32 degrees. So by so doing, you can get the molecular structure and molecular dynamics. But I was so intrigued by the analogy between this and the hemoglobin in your blood right now. Namely, here is the heme, and you have, this is, instead of benzene, you have porphyrin, and then oxygen, which regulates the muscles and gets stored, and the kinetics of it and everything is just bound to the metal of this particular porphyrin here in this environment of part of the hemoglobin. And there is a base here on the bottom. So to me, in a very simple way, because I want to understand the physics, I thought that the analogy between oxygen and the heme, it could be very similar to the iodine and benzene if we try to understand what's happening there and induce the electron, which is important for the oxidation, for the reduction of oxygen, and see what's happening. So we had a postdoc in a joint effort with my colleague Fred Anson and this center that Professor Norden mentioned. And we made a network that tried to mimic the protein network. And the reason we did not want to jump into something that is not clean, we want to make this network at our hand. We want to modify the hydrogen bonding, the network structure, so that's something that we can control. And then we have exactly the same type of the heme. And then the remarkable thing is that at room temperature, just like in your blood, at room temperature, about 80 to 90% of the system is bound with oxygen. So we are not doing this in an environment different from what's happening in situ in your blood. And now we can study on the femtosecond time scale, induce the charge separation, and find out how this oxygen is going to be liberated and what kind of forces that are involved, and would the oxygen recombine, and what time scales we're talking about. This is coming out, or came out, in Angewandte Chemie, and the results are just drastically noticeable. If we have the system without the oxygen and without the base, and we add the base, the dynamics is very similar, but the minute we add the oxygen into this, you can see now we're seeing what's called the negative absorbance. We know that the oxygen has been released in 1.9 picosecond. So this, and there is no recombination of the oxygen again in the heme pocket. So what we're trying to understand here now, by changing the environment and the molecular structure around this species, can we understand to optimize the system and create a very clear transition state. And for the experts, this actually is the first time that we enter now the transition state directly, rather than looking at a very slow chemical reactions that takes milliseconds, and all trajectories are smeared out without any coherence. And I was delighted to see a paper coming from the French group where they have just done the cytochrome oxidase, which is very important for respirations in your systems. And the remarkable thing is that the carbon monoxide moves between the two metal centers in a very similar way and a very coherent way in this network of molecular assembly. So if you look at many other applications, this is the one I showed on the first slide. Your eye right now is responding by this molecule retinal, and this experiment was not done by us. This experiment was done at Berkeley and also in Germany, and you can see clearly that the motion of this retinal molecules that give the signal into our brain is 200 femtosecond. There is beautiful and very important work on how the green plant or photosynthesis in general works. You're getting light from the sun, and you convert it into chemical energy. And until today, even though a Nobel Prize was given to the molecular structure of the reaction center, until today, we don't understand the dynamics. How does the electron move in the reaction center? How does the energy, once it's absorbed, moves in this system? And Professor Sundström here in Lund is one of the leaders in this area. In fact, this is a transparency from one of his reviews. And now we know the elementary steps. As light, the solar light is being absorbed and the energy is moving around here, and called the light harvesting 2 system, and at the end it ends up in this reaction centers where you can get chemistry to go. And the question is, what is the time scale for charge separation? Why does it move coherently? Because it's showing coherence behavior just like I showed you earlier. These are all very fascinating questions. In the DNA area, I am very much intrigued by this, and because we have studied earlier on of how this mutation in the DNA, what is the time scale and how the protein moves. And recently we learned, building on the work that is going on in Göteborg, Professor Nordin, where you actually complex these DNA at a given sites by electron donors and electron acceptors, and you try to learn of how electron moves. This is very important if it's true in terms of the speed at which it's going. It's very important for things like mechanisms for carcinogenic behaviors, and is the chemistry local or not local? So there is a lot of activities in this area. What about the future? Well, I know I'm running out of time, but I just want to tell you that there are two things, and I'll skip very quickly. One is that now we have the ability to look with atomic scale resolution, and on the time scale that they really occur. I wrote a conjecture paper. There was no experimental evidence at the time, but somehow it seems clear to me at the time that if we can shorten the pulses to get into the time scale of the motion of the atoms, we should also be able to control the outcome. So this is what it said: with sufficiently brief and intense radiation, properly tuned to specific resonances, we may be able to fulfill a chemistry dream to break particular selected bond in large molecules. This field, it's a whole field by itself now, but it's really in its infancy. We're all trying to find prototype system. We just published a paper in Science 2 years ago, which we saw an enormous selectivity and control. But is it general? We don't know yet. And we and other colleagues are working actively in this area. This is another area that I was very delighted that the Nobel Committee did not cite any of this. So there might be a chance coming back to Sweden, you never know. But this is an area where I believe is going to be extremely important for biological sciences. And we're pushing this very hard over the last 4 or 5 years. And that is, in addition to looking by all these tools that I mentioned to you, we're now converting light pulses into electron pulses. And for the experts in the audience, the de Broglie wavelengths of the electron pulse is much less than the bond distances in, say, in a protein molecules between the atoms. And so my ultimate goal there, which might take 10 years or 20 years, is that we have already successes with the small systems. But my ultimate goal there is, with my group and in the Laboratory for Molecular Sciences, is that we can see one day a total architecture of a protein molecules unfolding in real time, and to be able to understand what it means and what are forces, especially the so-called hydrophobic forces or lack thereof. This is going to be a very exciting area. All the experts in the field 4 years ago told me it's not going to work. And that, when they say that, that is the time for the young people in the audience. That is the time where you push on. And you know that you are on the right track. Because the reason they say that is because, of course, it's based on what we know at the time. But this was the first diffraction image obtained from that molecule, an isolated molecule, with a time scale of about 5 or 10 picosecond, not femtosecond. And the signal, of course, is very primitive, but this was the first time that it's being recorded in 2 dimensions on a CCD camera. Well, I'm happy to report to you that this year, this is the diffraction image now we can get. We got about 1,000-fold increase in the sensitivity, and we also have at least a factor of 10 improvement time resolution, down to about half 500 femtosecond, and we are on our way to about 50 femtosecond, which we believe we will be able to take diffraction images, get bond distances, and go back into the architecture of the molecule as they actually change. And this was published recently, settling a very important problem that the organic chemists talked about for a long time. If you take a molecule like this, I took this from Roald Hoffman, who wrote a commentary on our paper. So it's his drawing, but it's my work. So here is the molecule. The two bonds are broken, but then in between, would you ask, is the architecture of the molecule, is the bond is in this direction, or is the atoms in between, the so-called bridge structure versus non-bridge structure? And so by looking at the diffraction images here, we can actually prove that this is not the case, and this is a classical structure. And the reason the original idea was not right is because the time scale for the rotation around the single bond was slower than was thought about before. So this is an area that I'm quite excited about. While getting to the conclusion section, which will take another half an hour, but it will not take half an hour. But I think this summarizes really what I want, the message, the take-home lesson that I want to say. I think we have witnessed really a revolution by many colleagues at the beginning of the century, and many, many scientists have worked in order to bring us into the millisecond and microsecond. As you can see, there is a break here. Now we are at a time scale where we can see the atoms moving. And this is quite exciting because it's fundamental. It's shorter now than the time scale of any molecular vibration. Even a hydrogen molecule, the lightest of all, is taking 10 femtosecond to vibrate. And so you're looking at the molecular vibrations now covered, the molecular rotations. And if you're looking at physical systems, we even did collisions in liquids. We can freeze them on that time scale. You can look at chemical reactions, as I mentioned to you, complex one, and I give you a flavor of what's happening in the biological area. This is perhaps for the future. The biological time scales here are, theory is ahead. Theory is doing very well on the very short time scale in computational dynamics, but it's having a hard time as it goes on to the very long time scale. Right now, in terms of what we want to do, we're doing very well up to the picosecond or so, or half a picosecond. But with these new techniques, I am convinced that we will be able to get primary functions and elementary motions on these systems. And I am not also convinced of the words that is written in almost in every review article that biological activities are going to be milliseconds and microseconds, because the same thing was said about chemical reactions. So if there is anything to be said about the spatial resolution, is now we're really having the atomic scale resolution in both structures and dynamics. Well, I think that I give you the impression that I deserve the Nobel Prize by myself. But this really is not the honest truth. And this is truly from the heart. There have been so many people that have contributed into this. First and above all is my group at Caltech. And this will be published in the Nobel lecture. Nobel paper, and this is truly international. With all of these dots that you're showing here, actually, it's a glue of dots because we couldn't put all these dots in a clear way. So there are so many people here, close to more than 100 people have contributed and came from all over the world. And I just simply represent truly their effort to you today in presenting this contribution that made in the Nobel Prize. The latest snapshot of these people is the latest snapshot, and it's dark a little bit, but there is a message here of how international and wonderful science, as the Secretary General of the Swedish Academy was pointing out yesterday. From Malaysia, from America, from Korea, from Denmark, from India, from Germany, from China, from Berkeley, America, from Lithuania and Sweden, from Korea, from Egypt and America, from Germany, from Russia, from China, from Switzerland, from Taiwan, from Korea, and from Italy. You can't have it any better. Thank you so much. Fantastic. Fantastic. Thank you very much.
We thank Professor Zewail once more. For a moment, I wasn't sure whether I was in a physics lecture or a chemistry lecture, but we realized the importance for chemistry. In closing this session, I want to remind you just that we reassembled here at 2 o'clock to hear Professor Mondell give his economics lecture. And in this, I close the session.
Thank you very much. Thank you.